Hello everyone, welcome to today's video. Today we'll be covering the law of cosines. So in our last video we saw that if we knew some information about some non-right triangle, we were able to still solve the triangle unless we only knew two of the sides and the angle in between them. Now we are prepared to solve those triangles as well. So we will derive the law of cosines using the generalized Pythagorean theorem. And then we'll solve some triangles using the law of cosines, and then we'll use the law of sines to solve the rest of the triangle. We'll look at an application problem, and then we'll look at Heron's formula, which is a way to find the area of an oblique triangle. So let's start off here with a motivating idea. While the law of sines lets us solve many oblique triangles, it does not solve triangles where the known angle is between the two known sides, like I just said. So an SAS, side angle side triangle. Or when all three sides are known and no angles, so side, side, side. To solve these, we're going to use the generalized Pythagorean theorem. So to do that, we are going to draw an oblique triangle here, but first I'm just going to put it on a set of axes to give us something to look at here. So let me get some axes on the page. And then we're going to draw our triangle in, so let me just pop in some sort of angle here. And I'm starting it with it at the origin down here. That is on purpose so that we can have something nice to look at here. And then let me just drop in another side there, and then our third side. There we go. So there is our oblique triangle, and I've centered it at the origin. So I'm just going to label this point up here as x, y. So let me label the rest of this triangle. We'll call this side alpha, or this angle alpha rather. And we'll call this beta, and we'll call this gamma, which means that this must be side A, this must be side B, and this must be side C. So just labeling our triangle in the standard way here. But this allows us to drop down a perpendicular here to create a right triangle. And since I'm placing this where x is, since I labeled this point up here xy, I know that this whole distance down here is going to be x, which means that if I'm just looking at this littler triangle here, this distance here is going to be x minus c. So if you add those together, c plus x minus c, you get x, which is that total distance there. So I'm just splitting apart that right triangle into two components in its base there. So yeah, now we have this smaller right triangle here as well. Let me see if I can do that a little bit better. All right, so now we've got our right triangle here, this little one, and maybe I can make this other side blue as well, just so that we can have some visual difference here. So let me remind you that we can define x and y in terms of sines and cosines. So if I'm looking at this right triangle here, this big right triangle, and I'm looking at my angle alpha, we know that the cosine of alpha is going to be equal to the opposite side, or I'm sorry, the adjacent side, which is x, over the hypotenuse, which is b. And if I solve for x, this is going to give me x equals b cosine alpha. So we're going to want to use that here in a second, and I can do something similar, knowing that the sine of alpha is going to be y. The side is y, since we have a height of y. Y over b, our hypotenuse. So this is going to tell us that y is equal to b times the sine of alpha. So we can use these relationships as we try to investigate solving this triangle here. So next we're going to see if we can't solve for a. So if we can't solve for this side here. So we know from the Pythagorean theorem, looking at this smaller blue triangle here, that a squared is going to be equal to x minus c squared plus y squared. So just the two sides of that smaller right triangle there. If I make a substitution, we're going to get that a squared is equal to, we know that x is b cosine alpha minus c, all being squared, plus, and we know that y is going to be b sine of alpha, also being squared. So now if we do a little bit of algebra here, we're going to get, maybe just give myself a little bit more space because this will expand a bit. We're going to get b squared cosine squared alpha. So I'm just foiling out this term here. Then we're going to get minus 2b times c times the cosine of alpha. And then we're going to get plus c squared. So that is just foiling that out. And then at the end, we're going to have plus b squared sine squared alpha. Just barely enough room to squeeze that in there. So now as I'm looking at this, I might notice that we have a b squared cosine alpha and a b squared, what did I say? B squared cosine squared alpha and a b squared sine squared alpha. Now if I put those together, I'm going to factor out the b squared as I do this. And then I'm going to have cosine squared alpha plus sine squared alpha. And that is nice because that is our general Pythagorean identity. So that's just going to be equal to 1. And then to write the rest of this out here, we're going to have, I'm going to write the plus c squared first, and then I'll write the minus 2bc times the cosine of alpha. So like I said, we know that this is all just going to become 1. So putting this all back together here, remember that this was a squared that we were looking for. So we've got a squared is equal to b squared. All of this became 1, so no need to write that. Plus c squared. Hey, that's looking a lot like the Pythagorean theorem, doesn't it? But then we have this extra bit at the end here. So we need to subtract off 2 times bc times the cosine of alpha. So there we go. Here is a formula to be able to find a, the side across from alpha. If we know what alpha is, we can take the cosine. And if we know what the sides around it are, b and c, now we have a formula that allows us to do this. So we could do a similar argument to find the other ones, but let's go ahead and take a look at all of the law of cosines here. So here's the first one that we found on the previous page, that a squared is equal to b squared plus c squared minus 2bc cosine of alpha. A bit of a mouthful to say, but again, it starts off exactly like the Pythagorean theorem, and then you need to subtract off 2 times those sides times the cosine of the angle in between them. And that works for any of the other ones here as well. So b squared being equal to a squared plus c squared minus 2ac cosine of beta, or c squared being equal to a squared plus b squared minus 2ab cosine of gamma. If we do a little bit of algebra on each of these formulas, we can solve for these angles. Specifically, we're going to have to do an inverse cosine on these to actually solve for the angle. But this is just kind of a shortcut. And if we want to see how to get there, we could do a little bit of that algebra here. At least we'll look at this first one. If I add 2bc cosine alpha to both sides plus 2bc cosine alpha, and I subtract, a squared from both sides. From both sides, those are going to cancel. These are going to cancel. And what we're going to be looking at here is 2bc cosine of alpha is equal to b squared plus c squared minus a squared. And then if we divide both sides by 2bc, we're getting that the cosine of alpha is equal to b squared plus c squared minus a squared all over 2bc, which is exactly what we have here. So you can do the same algebra on the other ones and get those formulas as well. I'm not recommending memorizing all of these. I mean, we should know that the ones on top here, the ones on bottom, we can perform this algebra if we need to, but sometimes having the formulas here is just nice as well. So let me erase some of this here just to clean that up again. But I at least wanted to show you how to get from one spot to the other. So now we've got the law of cosines. Let's use it to solve some triangles. So here's our first one to solve. We've got an oblique triangle here. We're not told that this triangle is right, even though it kind of looks like it is. We will see that it is not as we solve it. We know that we've got this angle, which is 30 degrees, and we know the sides around it, which means that we're going to use the law of cosines here. So just as this thing is labeled, it looks like we know what beta is, so the side that we're going to be able to solve for is b. So here is what we will do. So I'm just kind of putting a box around the one we want, but we know that b squared is going to be equal to a squared. So a is 10. So 10 squared plus c squared, and c is 12. So 12 squared. And then we'll do so that is looking a lot like the Pythagorean theorem, just kind of in general. We don't have one side being the hypotenuse because none of these are hypotenuse, but it has a similar flavor as we start here. And then we do minus 2 times 10 times 12 times the cosine of 30 degrees. So as we keep working this out here, we're going to get 100 plus 144 minus 2 times 12 is 24 times 10. That's going to be 240. The cosine of 30 degrees is square root of 3 over 2. So we're looking at 244 minus 120. So I'm just doing 240 divided by 2 times the square root of 3. And that's b squared. So now we want to take a square root of both sides. Technically that gives us plus and minus, but since we're looking for a distance, we will throw out the minus version, and we'll get that b is equal to the square root of 244 minus 120 times the square root of 3. We'll put that into a calculator to get an approximation, and we'll see that b is about 6.013. So there we go. We've got our b value. This is going to be about 6.013. So now we've got all of our sides. Now we can use the law of sines to figure out one of the other angles here, and then we should be off to the races. So let's take a look here. Using the law of sines, so maybe I'll just write that down, law of sines. We know that sine of alpha is to 10. So alpha is what I'm trying to solve for here. As sine of 30 is to 6.013. That is the new side that we know now. And technically this will be an approximation since I did approximate 6.013. Technically an approximation here, so I should throw an approximation here as well. If I multiply both sides by 10, those will cancel, and we're getting sine alpha is equal to 10 sine of 30 degrees all over 6.013. Again, that should be about. We'll do a sine inverse here, and we will get that alpha is about 56.3 degrees. So alpha, label it in here, it's going to be 56.3 degrees. The last thing we need to find is gamma. We know that all triangles have 180 degrees in them. We know that one of them is 30 degrees. We just found that the other one is about 56.3 degrees. So putting that all together, we will get that gamma is about 93.7 degrees. So like I said, it looked like maybe it was a right triangle. These are never drawn to scale anyway, so I guess I shouldn't have trusted that, but 93.7 degrees is what we have there. So there we go. We have solved this triangle. We now know every side length, and we now know every angle measure. So there we go. There is using the law of cosines, since we knew two of the sides and the angle in between them to find the opposite side. Once we've got two sides, we can use the law of sines to solve the triangle from there. So let's take a look at another example here. Here we want to find the angle alpha if we know all three sides of this triangle. So I guess we're not asked to solve the entire thing, but just find the angle alpha. So let's just draw a triangle here so we have something to look at. Let's make it a little bigger. There we go. There's our triangle. We will call, I labeled it different on my picture here for some reason. I'm putting alpha over here. So we'll put alpha there just so I don't look at something wrong and mess it up. So we know that A is going to be 20. We know that B is going to be 25. Oh, I guess I put it on the bottom. I labeled this one all weird. And C is going to be 18. And what we want to do is find alpha here. So for what it's worth, this is beta and this is gamma. We know all the sides here, so what we're going to do, we could just use one of our regular old law of sines here, but since we're trying to solve for alpha, let's just use one of these alternate versions here that are already explicitly solved for. So I'm going to use cosine alpha, which is what we're trying to find. alpha, that is, and we've got that is equal to b squared, so 25 squared, plus c squared, which is 18 squared, minus a squared, which is 20 squared, all over 2 times b, which is 25, times c, which is 18. All right, and we will put that into a calculator, and we are getting that cosine alpha is equal to exactly 0.61, as it turns out. So not even an approximation there. We're going to have to approximate anyway, because now we're going to take the cosine inverse of both sides. So this will be our first cosine inverse, I think. Maybe not. But we're going to take the cosine inverse of both sides here, so that those undo each other, and we'll get that alpha is about, putting this into a calculator, 52.4 degrees. Now, when we were using sine inverse for the law of sines, there was an ambiguous case that we had to look into. What is nice here is that there is no ambiguous case. So let me just write a note here. So note that cosine inverse of alpha returns angles between 0 degrees and 180 degrees. So if you think about our unit circle example here, if we're thinking about inverse cosine just gives us the top half of the unit circle, which is from 0 degrees to 180 degrees, or from 0 to pi. So that means there is no ambiguous case. Because for sine, this is for cosine, for sine of alpha, it returns angles between negative pi over 2 and pi over 2, or from negative 90 degrees to 90 degrees. Since negative 90 degrees doesn't make any sense in terms of an angle of a triangle, that's where the ambiguity comes in, because you could think about maybe coming all the way back around, and now there's some obtuse angle. There's some thinking to do there. But that's the reason that we do not need to check for an ambiguous case here. There will only be one solution, because the cosine inverse only returns angles in a range where there is no ambiguity. We're always going to get the angle that we desire. So there we go. Alpha in this case is 52.4 degrees. And we don't need to worry about anything more ambiguous than that because of the way that cosine inverse works. So let's take a look at an application problem here. So this addresses triangulation, if you've ever heard that word triangulation before, maybe even in a movie or a TV show or something. But many cell phones with GPS, an approximate location can be given before the GPS signal is received. This is accomplished through a process called triangulation, which works by using the distance from two known points. So suppose, there are two cell phone towers within range of a cell phone. So the towers are located 6,000 feet apart along a straight highway running east to west. So I'm going to just try and draw that picture here. Here's my highway running east to west. And we've got one cell phone tower over here. And we've got another cell phone tower over there. And we know that there is 6,000 feet in between them. So 6,000 feet running between these two cell phone towers. The cell phone is north of the highway. So we'll just draw this cell phone somewhere out here, north of the highway. Based on the signal delay, it can be determined that the signal is 5,050 feet from the first tower. So if I'm looking at this distance here, this is going to give me 5,050 feet. And from the second tower, it's 2,420. So if I'm looking at this distance here, this is going to give us 2,420. We want to determine the position of the cell phone north and east from the first tower. So say I don't know, now I'm making things up, but say there's some fugitive out there and we know they're hiding in a field and we can find their cell phone location from here. So, if we're on this highway, how far would we need to travel down this highway, and how far up, once we find that spot, would we need to travel to find our cell phone here? So that's what it's asking when it's asking to determine the position north and east of the first tower. So we're going east, and then we're going north to figure out where this cell phone is. So we've got a right triangle here that we could use, but we don't know any of the angles that are part of this right triangle. So maybe we label this alpha, and if I knew what alpha was, then I could use things I know about sines and cosines for right triangles to figure out maybe what this distance y is here. We don't know what this distance x is here. That's one of the things that we need to find. So that keeps us from just using a more straightforward technique. But I can view this bigger triangle here and use the law of cosines, since I know this big side and this big side, and I'm trying to find something about the angle between them, and I know the opposite side here. So that is the idea. We're going to use the law of cosines. The one I'm going to want to use here, so cosine alpha, I guess, is what I'm using, since I labeled as alpha. So I'm going to look at this guy here and look at cosine alpha, which is what I'm trying to solve for, is equal to b squared. So I guess I will label this one b and this one c, just to give us, that one's got to be a, sorry. That's across from alpha. This has to be a. So this one must be c. So I know what a and c are now. Okay, b and c rather. So if I'm, well, I guess I need to know all of them, but b squared is going to be 50 squared plus c squared, so plus 6,000 squared, minus 2420 squared, all over 2 times b, which is 50, times c, which is 6,000. So we will put that into a calculator. We're getting that cosine alpha is about, what do I have here? 0.9183. I would try and keep these approximation or the full expansions in my calculator as I'm working these out precisely. But now if I take a cosine inverse, so we're going to get that alpha is equal to cosine inverse of 0.9183. And again, we don't need to worry about some ambiguous case here because we're using cosine inverse, and that will always give us an angle between 0 and 180. And we're getting that alpha is about 23.3 degrees. So we know that this is about 23.3 degrees. And now that we know that, we can use just our standard relationships of sine and cosine for right triangles to figure out where this cell phone is. So we know that sine of 23.3 degrees is going to be equal to the opposite, which is y, over the hypotenuse, which is 50, which is going to tell us that y is about, so multiply both sides by 50, plug it into a calculator, we'll get that y is about 1997.5. And we are getting, if I use cosine of 23.3 degrees is equal to, now I'll call this distance here x, just this east distance here, x, the adjacent side, over 50. Multiply both sides by 50 and put that into a calculator. We will get that x is about 4638.2. These are feet, by the way, feet. So if we want to go find this cell phone, we would walk east from the first cell phone tower along this highway, 4,638.2 feet, and then we would walk north 1,997.5 feet, and we should find the cell phone as long as it's not moving. So that gives us how far north and east, and it also determines how far it is from the highway. It is 1,997.5 feet from the highway. So there we go. Using the law of cosines, we could figure out the angle that we needed here. Then we abandon the oblique triangle and focus on this right triangle. But now that we know one of the angles, we can figure out the rest of the information we need. So there we go. All right, we will finish this off here by looking at Heron's formula. I'm not providing a proof of this. It's not super difficult, but it is cumbersome and long. So if you would like to see a proof of it, there are a bunch of them on YouTube. Just type in Heron's formula proof and you will find find some out there. But essentially the idea is we can break any oblique triangle into two right triangles. We can find some relationships. If I call this like B1 and B2, and I call this H, we can start building different right triangles, looking at different relationships to put this kind of all together to get the area. So I encourage you to look it up if you are interested, but for sake of time and brevity, we will just look at using it here. So Heron's formula finds the area of oblique triangles in which all the side lengths are known. So we will let S be 1/2 of the triangle's perimeter, also known as the semiperimeter. So here I've got a specific formula for S. Hopefully that makes sense. We'll just find the perimeter, which is the numerator here, divide it by 2, and then that's 1/2 of the perimeter. So we call that the semiperimeter. We can find the area is equal to the square root of the semiperimeter times the semiperimeter minus 1 of the sides, times the semiperimeter minus 1 of the other sides, times the semiperimeter minus the third side. Put that all together and take the square root, and we should get the area. So let's look at an example here. There's nothing too out of control to see, but if I want to find the area of this, we're going to be looking, well, the first thing I should do is find the semiperimeter before I start looking at the area. So the semiperimeter is going to be 7 plus 10 plus 15 over 2. That's going to give us 32 over 2, which is 16. So our semiperimeter is 16. I know this formula, you might think you need to plug it in, but as soon as we get S, we don't need to plug anything in. We'll just plug, we will plug 16 in, but it's nothing more complicated than that. So now that I want to find the area, this is going to be the square root of 16 times 16 minus 10 times 16 minus 15 times 16 minus 7. So that's going to give us the square root of 16 times 6 times 1 times 9, which is the square root of 864, which is about 29.4 square units. So there we go. We've got that the area here is about 29.4 square units. I guess I can write units squared. So there we go. There is Heron's formula in action. We'll find the semiperimeter, then we'll plug it into this formula that involves the semiperimeter and do a little computation there. So with that, I will leave you to go practice some exercises here. If you have any questions as you're working, please let me know, and I'll see you in our next video.